I didn't. No, I didn't. I'm gonna let them know that it's wrong.
So, very, very, very quick little overall sketch of what the heck we did yesterday. We know this formula here. And we use this formula, and that of course gives me an estimate of where the x is. So, using this outline, I don't normally know this, right? So if I've got something I'm studying, I don't know what the mean is. I got to go out there and do what to figure out, get a feel for what the mean is. I do what? Take a sample, right? So if I don't know the average pollution parts per million of this certain lake, I go out and take water samples from the lake, different times of day, different parts of the lake. And from those samples, I can get an estimate, what's called a point estimate for the actual average, for the actual mean. So this is what we call a point. So the book says point estimate. This is what it means, just the average. Now from there, what we do is we know that that's almost guaranteed to not quite be right, but it should be close if my sample was nice and randomly selected. So if I go up and down a certain number of steps, well, how many steps do I want to go? Depends on how confident I want to be that I catch the real average. So there's a real average sitting somewhere. We take a sample and we build an interval around it. So if I build an interval that catches 90% of the information, then I'm 90% confident that the real mean falls in my interval, that my interval catches that real mean. So that's the idea from what we did last time. So what happens here is, since I took a sample, what's going to happen here? I took a sample, I'm doing something with the sample means. So I've got to take this and change it. I like it. This part is called the what? Error. So I want to go up and down. I'm going to go up so much and down so much. And if I catch, for example, 90% of the data around that X bar, then I'm 90% confident that that interval catches the real mean. So this is known as a confidence interval. It's crazy. We then took this error and we solved it for n. So we got an idea of how big a sample has to be within so much. So if I want to be within 7 centimeters of the true distance that a golf ball travels on a certain course, then I can figure out how many golf ball strikes I have to look at. This will tell me how many I've got to actually sample. How are we doing that? So I call this a feasibility study, because if this ends up being, 78 million, we probably isn't feasible to actually do that. But if it ends up being 300, okay, maybe I can handle that. I can do that many samples, that big of a sample. So that's what we did yesterday, or not yesterday, but last time. Building off of this, so what I'm going to do, I want to make sure you guys understand. I'm going to skip section A2 for right now. We're going to come right back to it, so don't get excited. I'm not throwing it out. I just always disagree with every textbook, always, in my opinion, puts it in the wrong order. Section 8.2 gives us an entirely different distribution. So that's why I'm like, why the hell would I do A2 before I did A3? A3 still uses the standard z-score distribution. So it makes more sense to me to do A3 first. Okay. So this is what we did yesterday. Let's do a very quick example. So what have I said? I took a sample, take 78 people, find average age of 39.2. We know sigma is, what you got, Chip? 11.09. Right, everybody knows that. It's just too obvious to even talk about. Find the 90% confidence interval for the true mean age. So, I went through this derivation of where this formula comes from, because that's where the work is really involved most of the time. Once I create the formula, then it becomes kind of a plug and chug situation. I hate teaching plug and chug, that's crap. You try to figure out why it makes sense, and that's where most of the work goes. Now it's really just plugging and chugging. They tell me X bar, sweet. They tell me sigma, sweet. They tell me N, sweet. So the only thing I don't know at the moment is Z. I don't know Z. Of course, I'm never going to know the mean, right? That's too bad for me. I'm never going to know what the real mean is. Normally, I just don't, because I can only use samples, but I can at least estimate what it looks to be. So how do I get the Z-score? Z-score is the only thing I'm missing. Why am I allowed to use Z-scores here? Why is it normal? Yeah, n equals 78 greater than 30. Central limit theorem says, sounds good. Go. Oh, shit. 30 is a magic number. Get above that, and you know it's normal enough. When you plot the sample means, it becomes normal enough. How do I get the Z-score then? I know I'm allowed to use this. It's going to be a 90% confidence interval. Some guys might remember, you can just look at the little baby chart. What does it say? 1.645. Alright. And the old-fashioned way to do this, if I give you a number that's not on the little baby chart, you have to do this. Bless you.
Thank you.
What area would be in that tail if there's 90% that I want to catch here? What area would be down there? 5%. Because there's 10 outside, so there must be 5%. If I look up 0.05 in the Z-score chart in the area, it'll be a little asterisk, and it'll take me out to 1.645. So just in case I give you like 89% confidence interval, and you know me, you know I'm going to do that. I took a class specifically in grad school about being a mean math teacher, and I made it A+. So you know I'm going to give you an 89%. So you just have to do this. You got to figure out what's areas there, look it up, get the Z-score, plug it in. So now they have to tell me this, they have to tell me this, they have to tell me this, and they have to give me this so I can figure out this. And now it's just plug and chug. Plug and chug. Careful. So now we get 39.2, give or take this many standard deviations. Square root of 78. So remember, the plus or minus is in the formula already. Don't freak yourself out. You just put 1.645 in the formula. The plus or minus is already built in, because I want to go up and down. So my suggestion to you was to do this error first. What do you guys get for that? Uh-oh, what's up?
For the error, right?
For the error.
2.066.
Yeah, 2.066, let's say, or 2.07 really. I like it. Go out one more place than this. And now you just add this, subtract this, plus you. So you'll get 37.13 up to 41.27.
Yep.
Stop there for a second. So from what we've done, do our findings suggest that the average could be 42? No. Our findings seem to say that it wouldn't be 42. Are you guys with me? What chance is it that I'm wrong? Yeah, on any kind of given thing, it's going to be a 10% chance I'm wrong. All right, that's sort of not exactly right, but that's basically the idea. It would be 5% because it's just that one side, but oh well, it's okay. You guys kind of get the idea. So from our findings, it seems to suggest that it can't be up to 42. It can't be down to 37. So how do you say the conclusion? We are 90% confident that the interval 37.13 to 41.27 years contains the true mean age of whatever this was. That's all I said to you. So that's all you can write. Okay, all right. So if I made this 95% confident, what would happen to my interval? It'd have to get wider, because why is it this wide? Because it catches 90%, so that I'm 90% confident. If I want to be 95% confident, I got to catch 5% more. This is going to get bigger. And of course, if it was 95%, the z-score would get bigger. So that corresponds to this interval getting wider. I like it. I got you. All right. Yes, sir.
So in contrast to that, there was a question in the homework that was asking about when you increase the sample size, and do we just and that if you increase the sample size, technically the confidence interval should.
If you keep everything else the same, and I just increase the sample size, but everything else stays the same, what's going to happen to the error if this number gets bigger? It's going to get smaller, because we're going to be dividing by a bigger thing, which means my interval is going to get narrower.
Okay, and that's all we need to do.
It's a hard word to say. Narrower. Yeah, that's all you got to say. Just say that it would make the error smaller, so my interval gets smaller. And think about it. The larger the sample you take, do you feel more certain or less certain about what you find? More certain. So I shouldn't have to make as big of a confidence interval to cover my ass for the unknowns. The bigger my sample gets, the smaller my interval should get, because I'm more and more sure about what I see. If I take a very small sample and I get a mean, hey, it's really easy for me to be way off, so my interval's got to get really big to cover for that fact. But the bigger my sample gets, the more and more sure I am about what I actually saw, the smaller the interval can get. The less I have to cover my ass for what I don't know, because I know more because I took a bigger sample. Yes, sir?
So for this problem, you don't need to change the standard deviation to like the sample?
Right there. And be careful. It's not changing the standard deviation into a sample one. It's changing the individual standard deviation to a group. And it's built into the formula, right? It's all right? Cool. All right. So, guys, if you weren't here last time and that wasn't quite enough, then you got to come see me or watch the video. We're going to get it to the next level. Whole nother level.
This is the only thing that okay.
So I left this up here for a reason. I'm going to start here again. The same way we built the confidence interval formula for means, I'm going to start in the same place to try to build it for percentages. So guys, remind me, if I take a sample and I find a percentage who do something, so therefore I know a percentage who don't do that thing, what was the mean in that case? And what was the standard deviation? I like it. Now, so here's the thing we didn't know till now, just because I didn't say it earlier. This is a population percentage. So you remember every time it was like 11% of everyone is left-handed. It was always kind of like a percentage of everybody. So that was a population percentage. So just like we have a symbol for population mean and a symbol for sample mean, we have a symbol for population percentage. We already know what that is. That's just P. And here's the fun thing. So population percentage is P. Sample percentage is of course, p hat. You can play with that all you want to. Sounds like something I don't want to wear. Stuff like that. There we go. You don't want to wear the p hat. Sounds like you're in a boat, you forgot to bring the jug, you gotta use the hat. If you fish, you know what I'm talking about. So what I'm going to do now is I'm going to do the same kind of thing. I'm going to estimate mu. Now, so what's x bar going to be if I have n, p hat, and q hat? What's x bar going to be? N, p hat. I love it. So mu is going to be n times the population percentage. X bar is going to be n times the sample percentage. All right, we got to get over that whole p hat. And still, sigma is going to be square root of n p hat q hat. So if I replace the parts of this, so I'm going to estimate mu with n p hat plus or minus z, and in place of this I'm going to put square root of n p hat q hat. Should have never said that. All right, stay with me now. You guys kind of with me? We know that the mean is NP, but I'm going to estimate it. Just like we did earlier with mu, I replaced it with x bar because that was my best estimate for means. Plus or minus z times what the standard deviation is in this situation is square root of n p hat q hat. And this estimates NP. Is that cool? This estimates what NP is. That's going to give me an idea of what the mean is, NP. Now, what this doesn't do, what I want this to do is I want it to be a percentage, not n times a percentage. So I can just divide by n to get the percentage by itself. So if I divide by n, so p is approximated by p hat plus or minus. Now I can do something with this. Can I just cancel the n's? Yeah, probably gave it away the way I asked, hopefully. This n is under square root, this one is not, right? So you can only reduce them if they both have the same root. Oh shit, algebra has a purpose. But, what is n equal to the square root of? What do you take the square root of to get n? The square root of what is n? Square root of n squared is n. So I can replace n, square root of n squared. All right, let me stop there for a second. Why the hell would I do that shit? Because I can't do anything with these. These don't have the same roots. All right, let me rewrite it so it's got the same root. And now I can cancel an n out, right? Yes, ma'am. Do what? No, because n is the square root of n squared. It just is. So I didn't do something to it. I just rewrote it, made it look different, but it's the same thing. Does that make sense? But they aren't the same thing. So I can cancel n divided by n is 1. Square root of n divided by square root of n is 1. But square root of n divided by n, they're not the same root. I'm not allowed to kill them. They're not the same thing, so I can't cancel them. All right, baby. All right, you guys with me? You guys okay with this step? Square root of n squared is definitely n because n has got to be positive. So if anybody out there is freaking out about negative possibilities, it's impossible. Now I can cancel an n out. So I get p hat, give or take, z, square root of p hat, q hat, over n. So if I take a sample and I find a percentage of people who say something, then I know the percentage of the people that didn't say that thing or didn't do that thing. I can figure out an estimate for the percentage who did that thing or didn't or said that thing. Let's do an example instead of me trying to talk about it in general. Okay. So real quick, before I do an example, what part of this is acting like the standard deviation? This thing, right? So that's going to become important in the next chapter. It's going to show up again. So, if we take a sample of, what you got, John? 312 gross fund students. 102 of them say they're going to vote in the next election. 210 of them are going to just stay in bed in a fetal position, along with a large percentage of the rest of the country, so it's okay. Find the, let's be nice, 99% confidence interval for the true percentage gross amount students who will vote. So we took a sample, we find an estimate for what the true percentage is, and then we're going to build off of that, make an interval and say, it looks like I'm this confident that my interval catches the real percentage. It's exactly like the averages. The same conclusion at the end that I can write. Everything's the same. The formula just looks a little different because I don't have sigma anymore. I've got P's and Q's and N's. And they build their own standard deviation. So the problems always look like they don't give us enough information. But I don't need anywhere near as much information. Can somebody help me out? What would P hat be? Oh, thank you. Yeah, exactly. Don't make a big deal out of this. It seems like more and more people have trouble with percentages, but how do I get a percentage? The part divided by the whole. So 102 students out of 312 say they will vote. So 102 divided by 312. So 0.327 roughly. So always round these to at least 3 places. So if you want 6.9, even better. I love it. So 327 is fine, but 3.3, no good. You rounded it too much. Okay, maybe. Is everybody cool with that step? I mean, they're going to have to just give you 2 numbers, you divide them and find the percentage. So what's Q hat got to be? 673, I like it. 6, 7, 3, 9, 9, 10. Or just 1 minus in your calculator. What's N? 312. Be careful, not 102. Always a total number that I talked to or did something with. And what's the last thing I need to figure out? I got everything I need. I got N, P hat, Q hat. The last thing I need, of course, is Z. 99% confident. Is that on your little baby chart? Yes. That was being nice.
2.575.
Yeah. So this Z score is 2.575. And now it's just plug and chug. Let me see if you guys can handle this. So here's the formula again. The biggest mistake people make is a calculator error. Make sure that this whole thing is under the square root. Right? If you have a newer calculator, you can just let the square root grow over the whole thing. Don't leave it too early. So try to plug what we know into this equation. Let's see if we all end up at the same place. See if you guys are doing okay. Anybody get the error part yet?
0684.
A line. 0684. How'd everybody else do? You guys got that same thing? If you don't say anything, I assume it's a no. So, all right. If you don't get the same thing, now might be a good time to make sure that you know how to plug stuff in the calculator. I can come over and help you. Let me know if you don't get that same thing. Try to plug this in your calculator. Make sure you can get that same thing. If you have the newer calculator where the square root symbol grows, that's easy to tell that the whole thing is in there. If you have the older one and you have to open a square root here, open a parenthesis, just don't close it until there. Make sure the whole damn thing's in it. Otherwise you get way smaller number here. Alright? So then you got 0.327, give or take, 0.0684. So what do you get there?
2586. 0.3954.
Say cool. Yes? Alright, I like it. So then, from what we see, is it possible that more than 40% of Grossman students are going to vote? No, it looks like it's not possible. Now, of course, the chances I'm wrong here are what? 1%. So I feel pretty good about what we see. There's only a 1% chance I'm wrong. Or another way to look at it is, if each of you did your own sample, calculated your own confidence interval, 1% of those would not include the right percentage. It wouldn't capture the real percentage. That's the better way to look at it. So if you look at 100 confidence intervals that are made like this, on average, one of them is going to be wrong. It's going to have the wrong, it's not going to go far enough, it's not going to include the right number. Maybe. Okay, cool. And then, we can say we are 99% confident that the interval 25.86% to 39.54% contains the true blah blah blah. The true percentage of gross most students who vote. Okay. So let's do this. Let me finally shut up. And there are two sides to this. One side says section 8183. That's the side you should look at. The other side has weird looking stuff we haven't talked about yet. Okay. Try to do this. These problems here.
Thank you.
Sure.
Yes, sir. This one is the one that was there, right? Not this.
So for this equation, we're looking for just the true. But for this one, we're looking
For this one, the one we developed, we're looking for the true percentage.
Yeah.
That's why we divided the n out of it.
Okay.
We would take example
Gotcha.
after
Thank you.
Sure.
and that we try 60 and 8